Today, I'd like to provide you with a little insight into the world of lanthanoids and the related technology of the company Swiss Authentication. Here in the period system, we see the group of the lanthanoids, starting with the element lanthanum and extending to the element lutetium. The group of the lanthanoids has very interesting physical properties that are quite similar in all lanthanoids. First, I'd like to emphasize the temperature stability that extends up to 2000 degrees Celsius with lanthanoid mixtures. Lanthanoids are completely insensitive with respect to acids and alkaline. They don't bind themselves chemically with any other materials, which of course means that their specific material properties won't change. Depending on the application, Swiss Authentication is capable of manufacturing particle sizes that are typically between 30 micrometers and which extend far down into the nano area. For the first time, we've succeeded in manufacturing this lanthanoid mixture free from phase shift, which is enormously important for the later process. Special lanthanoid mixtures have a very special property, that of two-photon absorption. Two-photon absorption, in contrast to fluorescence, has the particular quality that this lanthanoid mixture is stimulated by longer wave light, and that it then emits shortwave and more energetic light. It sounds complicated, but in reality it's quite simple. One has to imagine that an electron is hit by a photon. Then this electron jumps up into the next higher energy level, but nothing happens quite yet. Only when a second photon strikes the electron is it propelled into the next higher stage. But it can't remain there, and from this point it falls back to where it came from. During this process, this energy is re-emitted in the form of an emission spectrum given off by this lanthanoid mixture. Here, the electron is hit by the first photon, then it jumps, is hit again, jumps a second time, then falls back again and finally gives off the emission spectrum. We have succeeded in using this two-photon absorption to create a vehicle for an intelligent solution. Through endowment, meaning the adduction of different materials and combinations of other lanthanoids, we've been able to alter this emission spectrum. That means, in the area of 200 to 1000 nanometers, we're able to create this emission spectrum specifically using our own in-house technology. Here in the black graph, we can see a lanthanoid mixture without endowment materials. We can only see two double peaks at this point and at this point. Thanks to our special manufacturing technologies, we have made this green line that you see, which is full of new peaks, and which is completely different in amplitude and wavelength. This newly created emission spectrum is now an unmistakable print, like a fingerprint. To sum up, this means that using the conventional and familiar technology of lanthanoid double-photon absorption as our vehicle, we're capable of creating a completely new substance that possesses a singular and unmistakable emission spectrum. The most commonly asked question is this system safe? It is very safe. Even through re-engineering, one wouldn't stand a chance of discovering the functionality of the emission spectrum due to the chemical and physical properties of the lanthanoid mixtures. Presently, it is absolutely impossible. Based on this illustration, we can clearly see how one could imagine this system. Here in this area, you see a wavelength of between 100 to 1000 nanometers. The area we consider as the relevant spectrum. The human eye, for example, can see from 450 to 780 nanometers. Anything that has a longer wavelength than red is in the infrared area. Anything with shorter waves is in the ultraviolet range. In this area, we have different peaks with different wavelengths and different amplitudes. This is a unique signal, which practically represents our key. The detector you see here, the complementary part, the so-called lock. Only when both fit one another is detection possible. This leads to a previously unattained level of security. These lanthanoid mixtures can be individually combined, and each customer receives his completely individual emission spectrum. It can be applied in very low concentrations, a few hundred or up to 1,000 parts per million in the target material, in the form of toner, ink, color, or screen print color. Our system is very cost-efficient when compared with other technologies that offer considerably less security. Our cost-performance ratio is very good. Our substance can be used in many different and virtually unlimited ways without changing existing material characteristics. Our material can be worked into or applied on the target material. It represents only a very small part of the material itself. It's also possible to treat all of the target material. Our lanthanoid mixtures are absolutely resistant to external influences such as temperature, mechanical damage, radiation, acids, and alkaline. They are very hard to trick or destroy. Now I'd like to show you what this raw lanthanoid actually looks like. For this step, I'll apply a small sample onto a glass plate. It is a very fine powder, similar in consistency to powdered sugar. Here you see the substance readily applied in finished products. Here we see a brass cartridge covered with a special sealant across the upper rim, in which the lanthanoids are present in a very low concentration. Just like here with this smart card, where there's a small amount of lanthanoid applied in a layer of screen print color, which is, however, more than enough. Now I'd like to demonstrate very simply how the detection takes place. I remove the sensor from the case and initiate the program with the check switch. Now you can clearly see the measuring diodes installed on the end of the sensor. Their only purpose is to determine whether or not the sensor head is active in the test. Let's take a look at the card. The first result. Then we move to the second point. Second result. And now we measure something completely different, namely this cartridge. And already we've got a result. With these lanthanoid mixtures, we can clearly see that with the appropriate laser stimulus, different colors are visible for the eye. Here in the first test, we can clearly see a red, and in the second test, with the same activation, a blue. And in the third test, a nice green. In this example, we can clearly see the measurement cycles of the blue LED and the actual measurement processes with infrared. The answer of the lanthanoids to the corresponding emission spectrum are these green segments. What you see here is a sample from before. When I draw closer to it with the sensor head, as you can see, nothing happens quite yet. Only when the sensor head realizes it's resting on the samples does the actual measurement process occur. Now you can see that impulses are being measured and the result will be displayed analogously on the screen. If I draw the sensor away from the sample, the measurement ends. Now I'd like to demonstrate to you that our lanthanoid mixtures are very stable indeed. First, we detect and sample and show the result on the screen. Now we want to see if everything still works after we've destroyed the powder. For this purpose, I'm going to take a cigarette and apply some lanthanoids to the tip. In the cigarette itself, we have temperatures of between 7 and 850 degrees Celsius. This is original sample number 1. Ashes. With its authentication technology, Swiss Authentication has developed a revolutionary security system. Because counterfeiting and forgery are rapidly increasing in all areas around the world, causing damages of many billions of dollars, it's becoming increasingly important to employ an individual, safe, efficient, and economical security system to protect products.